When Einstein was putting together his theory of general relativity, he hit a massive wall. Turns out the math he knew, the math that honestly most of us know, just completely falls apart when you start curving things. He literally needed a new mathematical language. So today we're going to unpack that toolkit he had to build to describe a universe where space-time itself can bend.
I mean, really think about it. Everything we know about geometry, about calculus, is all built on this idea of flat space. Drawing straight lines, using the Pythagorean theorem, comparing two arrows by just sliding one over next to the other. But what happens when the very space you're working in is curved, like the surface of the Earth? All of a sudden, your tools are useless. And that's the exact crisis Einstein found himself in.
So to see how physicists got around this, we're going to build their toolkit right from the ground up. We'll start by seeing exactly why our normal math breaks. Then we'll redefine what a vector is and meet its partner in crime, the dual vector. After that, we'll zoom out to see the bigger picture with tensors. And finally, we'll put it all together to invent a new kind of calculus that works perfectly, even when space is bent out of shape. Okay, let's dive into the core problem. Why does something as simple as a little bit of curvature throw such a huge wrench into our mathematics? Well, in the flat world we're used to, the basic rules are simple, right? Parallel lines stay parallel forever. But on a globe, just think about the lines of longitude. They start out parallel at the equator, but they all crash into each other at the poles. It's the same deal with vectors. You can't just pick up a vector from, say, New York and compare it to one in London, because the very coordinate grid has twisted and distorted between those 2 points. Right. So in flat space, moving a vector around is no big deal. Its x and y components just stay the same. But in curved space, whoa, it's a different story. To keep a vector pointing in what we'd call the same direction as you move along a curved path, its actual coordinates have to constantly change to compensate for the curve. This whole process is called parallel transport, and it's what completely breaks our normal way of taking derivatives. So to fix this, we need a new tool. The very first step is to throw out our simple idea of a vector as just an arrow and build a much more powerful, much more universal definition. So instead of defining a vector by what it is, an arrow with a length and a direction, physicists started defining it by what it does. In this new way of thinking, a vector is basically a machine. It's a machine that tells you how fast some value, let's say temperature, is changing if you decide to move in a particular direction. It's a directional derivative. And this equation right here is the formal math behind that idea. It says that the tangent vector, the arrow, is actually the exact same thing as the operation of taking a derivative along some path. Now, the real beauty of this definition is that it doesn't care about a flat grid. It works in any coordinate system you can dream up, which makes it absolutely perfect for general relativity. So once we have this new, super robust definition of a vector, we discover something cool. It has a natural partner, a kind of mathematical shadow that goes with it, and it's called a dual vector. Okay, if a vector is a machine for measuring the rate of change along a direction, a dual vector is kind of the opposite. It's a machine that you feed a direction into. You give it a vector, and it spits out a single number. Think of it like this. The dual vector is the set of instructions for how to measure any given vector. It's the ruler to the vector's arrow. And a perfect example of this is the gradient, which you probably ran into back in calculus. If you have a temperature map, the gradient isn't just one direction. No, it's an object that, when you feed it a direction vector, like due east, it gives you back a number that tells you exactly how fast the temperature is changing in that direction. The gradient is the classic dual vector. So we have our vectors and we have their duals. But how do you get from one to the other? The answer lies in what is arguably the single most important object in all of general relativity, the metric tensor. The metric is what defines the geometry of spacetime. It is the rulebook for measuring all distances and all angles. And the metric tensor does something incredible. It acts like a conversion machine. You take a vector, and by convention, we label its components with an upstairs index. You multiply it by the metric, and bam, out pops its matching dual vector, which now has a downstairs index. This little trick called lowering an index is absolutely fundamental to how all this math works. And here is that rule in all its mathematical glory. This equation just shows you the recipe. It's how the components of a dual vector, the A with the little subscript, are calculated from the original vector's components using that metric, G. This is the gear that connects a vector to its shadow. So we've built up vectors and dual vectors. But it turns out these are just the two simplest members of a much bigger, much more powerful family of objects that form the true language of physics, and they are called tensors. So what the heck is a tensor? Well, it's pretty much a generalization of everything we've just been talking about. It's a mathematical machine that can take multiple vectors and dual vectors as its inputs, and it always produces a single objective number, a scalar, as the output. And because it spits out a single number, it becomes independent of any coordinate system. And that's exactly what we need for the laws of physics. The cool part is, objects we already know and love are just different ranks of tensors. A plain old number, a scalar, like temperature, that's a rank 0 tensor. Our new vectors and dual vectors, those are rank 1 tensors. And that all-important metric tensor we just met, that's a rank 2 tensor, because it can take 2 vectors as an input to give back 1 number. And this, right here, this gets to the very heart of why tensors are so powerful. If you write a law of physics as a tensor equation, say tensor A equals 0, then that is a universal truth. If that equation is true for you as one observer, it's true for every single other observer in the entire universe, no matter how they're moving or what coordinates they're using. That is how you write the laws of nature. Okay, with vectors, duals, and the whole language of tensors, we finally have all the pieces. We can now go back to the problem that started this whole mess. How in the world do you take a derivative in curved spacetime? We can now build the ultimate tool, the covariant derivative. Remember this problem? To compare a vector at one point with a vector at another nearby point, you can't just subtract their components. It doesn't work. First, you have to account for the way the coordinate system itself has stretched or twisted between those two spots. You have to parallel transport one vector over to the other one's location before you can make a fair comparison. And this beautiful beast is the machine that does it. This is the covariant derivative. But look closely. The first part is just the normal derivative we're used to. That part measures how the vector's components are changing. But the second part, that's a brand new correction term. Those funny gamma symbols are called Christoffel symbols, and they're calculated straight from the metric tensor. Their entire job is to subtract out any changes that are only happening because the coordinate grid itself is curved. It's genius. So what does this new and improved derivative actually let us do? Well, it gives us a way to finally, truly measure change in a curved spacetime. And with it, we can ask a really profound question. What does it even mean to travel in a straight line if space itself is curved? The answer is, a straight line is a path where your velocity vector doesn't change, according to this new, corrected derivative. And this is it, the geodesic equation, the final payoff for all our hard work. It looks so simple, but its meaning is just mind-blowing. It says that the covariant derivative of an object's velocity as it moves along is 0. In plain English, an object in freefall under gravity is just following the straightest possible line it can through curved spacetime. Gravity isn't a force pulling on things, it's just geometry. It's things following the natural contours of the universe. This whole journey to reinvent calculus ended up giving us a completely revolutionary picture of gravity. And it really makes you wonder, what other fundamental forces, what other aspects of our universe are we completely misinterpreting just because we haven't found the right mathematical language to describe them yet?